We're going to look at integrating now. We have the integral from negative 1 over the square root of 2 to 1 over the square root of 2, 6 over the square root of 1 minus p squared dp. Now I'm going to show you what we're not looking at. If we had the integral of p over the square root of 1 minus p squared dp, then I would be looking at a substitution. I'd say that u is equal to 1 minus p squared, and so that du is equal to negative 2p dp. I would multiply and divide by a negative 2, and I would integrate using the power rule. We don't have that because we don't have a factor of p in the numerator here. So we have to look for new patterns. The place we're going to look for these new patterns is the new integration rules that we've learned involving these inverse trigonometric functions. So looking back at the work that we did, we developed some differentiation rules for the inverse trig functions, and those led us to integration rules for the inverse trig functions. Comparing what we have on the left, a square root of 1 minus p squared in a denominator, with what we have on the right, I know it's not going to evaluate to the inverse secant function because that has a factor of x next to the square root of 1 minus, and it's x squared minus 1, right? That's not even the thing. Here, we see that if we have an integral of 1 over 1 minus x squared in a square root dx, then that evaluates to the inverse sine of x plus c. So that's where we are. This is going to evaluate to an inverse sine function. We have that factor of 6 in the numerator, and so we're going to end up with 6 times the inverse sine of p, evaluated from negative 1 over the square root of 2 to 1 over the square root of 2. Evaluating the integral then using the second fundamental theorem of calculus, I get 6 times the inverse sine of 1 over the square root of 2 minus the inverse sine of negative 1 over the square root of 2. Now, as you may recall, I do not think of this really as the inverse sine of 1 over the square root. It's what is the angle whose sine is 1 over the square root of 2? And that answer is pi over 4. The angle whose sine is negative 1 over square root of 2. In the correct restricted domain for the sine function is going to be negative pi over 4. So we have, I keep having to change the parenthesis to a square bracket because we have nested symbols. And if I have parentheses inside, I should have square brackets outside. Just a little note. Inside the square brackets now, we have pi over 4 minus negative pi over 4. That becomes pi over 2. Times 6, we end up with 3 pi. Next up, we're going to evaluate the integral from 0 to the square root of 3 over 4 dx over 1 plus 16x squared. Looking at our new patterns here, we know that if we had the integral of 1 over 1 plus x squared dx, that would evaluate to the inverse tangent of x plus c. We don't have 1 over 1 plus x squared. We have 1 over 1 plus 16x squared. So I'm going to change what we wrote over here just a little bit and say that if we had 1 over 1 plus u squared du, then that would integrate to the inverse tangent of u plus c. We aren't going to have the c because this is a definite integral, but there's the integration rule. If I'm looking at the denominator as matching up with a 1 plus u squared, but I have 1 plus 16x squared, what must be u? I waited a beat there for you to answer it in your head. I hope you did. U is equal to 4x. So that when I square it, I get 16x squared, and it now fits this pattern. If u is equal to 4x, then du is equal to 4dx. And so I'm going to multiply and divide by 4. I then get 1/4 times the inverse tangent of 4x, evaluated from 0 to the square root of 3 over 4. Evaluating at these values, these limits of integration here, we end up with 1/4 times the inverse tangent, oh, I need a square bracket there. The inverse tangent of 4 times the square root of 3 over 4 minus the inverse tangent of 0. Of course, the inverse tangent of 0 is 0. And the 4's divide out, and now we're left with 1/4 times the inverse tangent of the square root of 3. At this point, I generally will turn to a unit circle and think about what's going on in the first quadrant with pi over 6 and pi over 3. Pi over 6 has coordinates the square root of 3 over 2, 1/2. The point, I should have said the point associated with pi over 6. The point on the unit circle associated with pi over 3 is 1/2 square root of 3 over 2. And I know that the tangent function is represented as the sine over the cosine. If I'm thinking about pi over 6, sine over cosine is going to put a square root of 3 in a denominator. If I'm thinking about pi over 3, sine over cosine is going to put the square root of 3 in a numerator. Therefore, the answer is going to be 1/4 of pi over 3, and so pi over 12.